Well, let's go back to questions and answers. And again, Remi, I am more than happy. I will edit out the parts where I interrupted you. And it's a good presentation, and so it'll be pretty seamless. But if yourself and Daniel are still open to doing questions, let me see. Does anyone have questions to ask?
I do.
Michael, go ahead. And can I get you to turn your camera on, sir?
Sure.
Oh, thank you.
Anyway, let's see. List. So regarding the epicatalytic diode, I think it's important to note that there is a range of temperatures at which it will work due to, so it, in a sense, it has a virtual heat sink, in a sense. Because the catalytic process still has some energy barrier to overcome, and it may be small, but that energy barrier must be considered relative to the average temperature, like the average energy of the particles in the system. And that the same idea applies if you're using thermionic emission, for example, things that have different work functions, and you make a vacuum chamber with one thing being carbon or tungsten or something, the other thing being lanthanum hexaboride, and then you still have to heat that up to a temperature similar to at least the lanthanum hexaboride electron volts.
Right. Yeah. Right. So yeah, I have worked with lanthanum hexaboride when I was in grad school to make Q machines work. So yeah, that's a good point. So the epicatalysis is fairly general. The idea, it works, it applies to plasma systems. Some of the early ones you can find in physics of plasmas from the mid-1990s that I worked on. The chemical ones with hydrogen, of course, you have to get up to about 1500 before you get to the threshold of the effects. But in the 2016 paper, Review of Scientific Instruments, we were able to show some initial kinds of epicatalytic behaviors at room temperature. And what we're currently doing with the help of a really talented experimentalist here at the university, David Miller, we're actually screening a large number of room temperature materials to try to bring down the epicatalytic effect from 1500 or 2000 degrees down to room temperature. I
have a bunch of recommendations later if you can.
No, Michael, we should chat.
I'll email you afterwards.
Yeah, that'd be nice. But so yes, you have, for things like hydrogen or dissociating potassium or cesium, you do need high temperatures, but there's no reason to believe that nature would be so cruel as not to allow room temperature epicatalysis, particularly since things like hydrogen bonding dimers like formic acid and acetic acid have bond strengths which are 10 times weaker than covalent bonds. So there's no reason to think that it shouldn't be possible at room temperature.
I would recommend reaching out maybe to Richard Maisel. He has a whole bunch of fuel cell stuff.
Oh, really? Do you know Dr. Maisel? I've read his book from front to back on.
Yeah, same.
Oh, really?
Also,
okay.
I'm currently working
well,
with.
Tell you what, Michael. Let's chat later because it sounds. This sounds like a really fruitful avenue.
Yeah, for sure. Yeah. And I have a number of, but the main point I wanted to make here, though, that is important to expand upon the definition of the epicatalytic diodes is that property of a virtual heat sink. It's very common in these systems. You have essentially some temperature below which nothing happens.
Oh, of course. No, you're going to have.
But then you have ambient. Yeah. Then you.
Yeah. I mean, if you look at the definition of things like equilibrium constants, and in terms of Gibbs free energies, you always have a KT in there, and so yes, you will always have you almost always have a threshold for these effects when it comes to epicatalysis, the superdegeneracy, and so on. However, there have been a number of proposals for second law challenges invoking things close to absolute zero with superconductors and phase transitions down there.
Well, yeah, you can get arbitrarily close, but I mean, it's all
sure.
The engineering is the important thing.
That's correct.
Yeah.
Yeah. No, you're right about that. That's right.
But there usually is that limit temperature somewhere.
Of course. I mean, for instance, in semiconductors, when you drop below about 100 Kelvin, you have carrier freeze out where your boron or phosphorus aren't either pick or knocking their electrons into, or giving their electrons into the lattice. And so once you have freeze out, everything becomes intrinsic and all your effects go away because you've broken because the asymmetry in the system goes away.
Yeah. Yeah. And then,
that's correct. You're
regarding
correct.
the thermal photovoltaic stuff, did you see MIT's paper about their 200% efficient LED? And
I didn't understand it. So maybe if you can send that along, I'd be happy to see. I'd love to see it again.
Well, to put it simply, they have this thing at a voltage. They bias the thing to a voltage. They apply a voltage such that it shouldn't be emitting any photons.
Mm-hmm.
But then the ambient heat is enough. So the voltage plus the ambient heat is sufficient to emit a photon.
Mm-hmm.
So that's the idea there. So you get like a piece. You get, it's weird. You get like a piece of the Boltzmann distribution like shifted up, but then you don't get something emitted from that looks purely like black body radiation. So it seems to suggest to me if you had like a multi-junction cell to harvest that very, very efficiently, you could probably get 60% efficiency, and then you'd have something that, I mean, they were saying this thing is a refrigerator or is a heat pump of a kind, but it may just straight up break the rules.
Yeah.
Well, now, if I could ask, and again, I apologize for butting in. I had said, this popped into my mind. I saw a magazine article a while ago where they proposed tidal generators on beaches, basically. And as the tide comes in, I saw a couple different, it was an engineer, and he'd said, one way is to have something that floats and the tide lifts it, and another way is to have something that compresses. And in both cases, it would turn a motor, right? But would that, in a case like that, I guess I think presumably gravity would be the driver, not ambient heat.
Oh yeah, no, those are not second law violators by a long shot. No, those are being driven by, well, whatever your tides are being driven by, either by gravitational effects or wind or whatever happens to be the case. But no.
Yeah.
Can I just cut in there? Those tidal generators, they would be driven by the decay of the moon's orbit around the Earth. Yeah.
Okay. Oh, that wouldn't make sense.
Yeah. That's what generates the tides.
Yeah, in fact, I just read that make perfect sense. I just read an article saying that there's a Chinese lake they created for a dam, and apparently this artificial lake is large enough that it actually slows the Earth's spin by like a millionth of a second or something. So,
yeah.
Okay. Well, let me
have some more questions and comments. So let's see. So yeah, I mentioned the thermionic emission system, which there was a paper about that I saw you guys, I think, collaborated with them. But anyway, what else? There was a fellow by the name of Patrick Kelly who unfortunately died a little while ago, I think, and he had a bunch of stuff up on YouTube. There was one system I didn't understand at first, but then once I realized it was operating this sort of way, it might be interesting to look at. It was literally just a bunch of buckets upside down catching air bubbles pumped under water. And what I think is happening there is as the air is floating up to the top, it's expanding, which makes the force, it's displacing more water as it goes up. Which means that it's cooling down. It may be harvesting ambient heat that way. And they were saying they were actually getting a decent amount of energy out of really big ones. At least that was the reported thing. A small other weird system, but to the core of this thing, I think it's important. Most of thermodynamics it's built upon the theory of ergodicity. And not all systems are ergodic. We have a bunch of counterexamples that you guys have worked on, that other people have worked on. But that's really where you have to go. If you study ergodic theory, there's the mathematical formalism for statistical mechanics and then thermodynamics. And you have to start there and build up, or you have to restart there and build up from something called, what was it again? What was the name? I'm blanking for a second. I had it written down here. Ramsay Theory, that was it. It's a more general case that describes the mathematics of non-ergodic systems as well as ergodic systems.
Yeah. Well,
I'm sorry.
And also, sorry, I didn't mean to interrupt.
No.
Yes.
Okay.
Well,
Michael, something else to look at is that nature provides a number of naturally occurring metastable state systems, which are thermal metastable states. So if you have something like we were investigating self-resonant semiconductor electromechanical oscillators, which use the electric field associated with the p-n junction. It turns out that nature is loaded with systems where you can let's say you have some sort of capacitor plates which are made out of connected somehow to make a diode or something. You'll have an electric field between these plates which stores energy. I mean, electric fields have an energy density. Electric fields have an energy density equal to the permittivity of free space, electric field squared divided by 2. And that energy can be used to actually accomplish electromechanical motion. But the thing is that the energy stored here is completely thermal, and you can show it. You have a KT factor that you've always talked about in the expression for this system. And when these plates come together and short out, springs can pull them back apart and they can recharge and close again. And you have basically an electromechanical oscillator, which is purely thermally driven. But it's because you have metastable states that nature naturally gives you, that you can go from a high energy to a lower energy state by changing the boundary conditions of the system. Once you extract your energy from that change, it can drift back to its high energy state again purely by thermal means, because that's its equilibrium state in that particular configuration. So I think that's related to your ergodic theory example, where the world is not the thermodynamic limit. The world is not infinitely large. There's not an infinite number of particles. There are boundaries, and there are a finite number of particles in it. And as a result, if you manipulate the boundary conditions and play the system against itself, in other words, you use the first law against the second as basically a club, and nature will accommodate you now and then. And so there needs to be a shift in the overall thermodynamic thinking of most physicists and chemists, for that matter. But they think of it in such general terms. They don't see the particulars, and they don't see the non-ergoticity of systems. They don't see the effects of the boundaries and how they store energy. But this is a fact of life.
Well, so by the way, have you seen the work at the University of Arkansas on the graphene energy harvester?
Yes, I have.
Good.
Yeah. Well, Michael, if it's okay, let me mute you out for now. And thank you again, sir. And I want to go to Remi. Remi's been patiently waiting there. Sir?
Hi, Daniel. I just wanted to know your thoughts about the fluctuation dissipation theorem and how it's usually seen as an argument killer to diode rectifier devices, to fiber magic devices. The idea that what you get, you use on the roundabouts.
Well, again, the fluctuation dissipation theorem is sound insofar as it's stated. Fluctuations that you naturally have in systems in terms of thermal and density fluctuations, these are natural effects of the system. These are directly related to the dissipative things like viscosity. That's unquestioned. But that doesn't really answer the question as to whether the fluctuation dissipation theorem is what it says, but that doesn't mean that it somehow derails or makes impossible energy storage at boundaries. In fact, it would tend to support it, I would assume. After all, it's based on the second law itself. So too much of I call this the ideal gas syndrome, and that is most physicists go to the ideal gas and say, look, you can prove the second law for the ideal gas. That's not hard to do. You simply follow a bunch of particles around inside a chamber, and you can show that PV equals NKT. So what? The world is not an ideal gas, and it's much richer than that. And so when people say that the second law has been proven, that's nonsense. It's nonsense on multiple levels. First of all, the second law is only true is true only can only be proven for a limited number of systems. Number two, it's epistemologically unsound to claim the second law is not violable, because the second law has to be violable if it's a true law. Laws are axioms of nature. That's what a law is. It cannot be proven. That's what it means to be a law. It's like trying to prove the axioms associated with Euclidean geometry. You don't prove these things, you assume these things. And the reason why the second law is assumed to be true is because it's seen to be true in all systems up to the present. But the thing is, it's not true. That's not true either. There are systems now which indicate, like the Arkansas group, like the epicatalysis experiments, some of the stuff by Jerry Pellegrini, some of the work now by Garrett Medell, indicate the second law is not absolute. All you need is one counterexample to it to show that it's not an absolute law. But the scientists tend to go back to the ideal gas law and presume that that if it works for ideal gases, it works for everything. But it's not true.
What you're saying is that they're basically setting up a bit of a straw man, and the fluctuation dissipation argument is a bit of a straw man. It's saying that with no measures, you put a diode on a tabletop, it's not spontaneously going to get hot at one end, cold at the other. Well, precisely because you're not doing anything to it. It will, once you design it to do something. It's a straw man argument, isn't it?
It's trivially true. That's right. And when I say trivially true, I'm not saying that it's not useful. I mean, it's true. It's true in general, but for whatever system you want, up to a point, but not for every system. Not for every system. And another great example of that kind of thinking is the Maxwell demon, which was invented by Maxwell as kind of a thought argument that he posted in a paper to a guy named Tate, in a letter to him. And that thing has lived on and on and on. And the scientific community trots this poor demon out every few years and whips it in the public square just to show the second law can be beaten. But the Maxwell demon was never a serious challenge to the second law and never will be. From the get-go, it had so many things. First of all, what does this demon look like? How do you build it? How do you keep it from having sticky fingers? How does it see? There are so many problems with it that it never had a serious chance of breaking anything. So if you show the Maxwell demon doesn't work, you haven't showed much of anything. The zombie idea is completely different in the sense that you're now using natural processes which don't think and don't have to go through any kind of thermodynamic cycle of thinking and forgetting, which creates the entropy. And as a result, things naturally occur on their own. And this occurs because zombies are big and stupid and blind and dumb. They don't have to think. They're big enough that they accumulate energy at their boundaries. They use natural processes. They are exactly what the Maxwell demon isn't. And the zombie has never been slain. And there are too many examples of it now to ignore. So
could I just ask you one further question? I won't keep other people up. What do you think about the sea change in thinking? And what you sort of hinted that the physical review is beginning to consider papers in this area. It's a bit like the whole cold fusion debacle, when for a certain amount of time they accepted them and they refused any new papers. Do you think the mood music is changing?
Well, the news media follows the scientific consensus. When it comes to journalism, the one thing they don't want to be is embarrassed. So they rarely go out on a limb. So Scientific American will publish articles associated with 11-dimensional or 23-dimensional spaces, whatever happens to be vogue this week, without a problem, because it can't be proved wrong. On the other hand, if you actually had evidence for second law breakdown, they wouldn't publish it because it would jeopardize the reputation of the journal. So there's a lot of that involved. I've been told by editors of journals at times, I won't name the particular editor because I respect the guy in general, but he told me, even if this was accepted by by the reviewers, even if it was correct, I would not publish it because it goes against the second law. That's how firm this injunction really is. It doesn't matter whether it's true or not, which is why I've been arguing lately that we need to go beyond the scientific community for these kinds of events, because the scientific community is not going to budge, at least in the short term, over it. It's not. It just won't. And you can go back to Thomas Kuhn and the Structure of Scientific Revolutions. If you've ever read that, you'll know that this is the way of the world. Science is not immune to psychological, anthropological, and sociological pathologies that you see in other parts of life and religion and elsewhere.
I think what they're going to have to justify is the huge sums of money spent on conventional science, say things like hot fusion and so forth. it's going to come to a point where it won't be sustainable by the public. They'll say, well, haven't you guys done it already? You know, it's been 6 decades and probably $1 trillion. We want to see something. And I think that's going to ultimately break them.
Well, guys, we're at the top of the hour. So I guess what I should do is, and we could go to open discussion after this. Maybe Tom Vallone, if he's open to it, Tom could present his thing. But I do want to, again, I want to thank Daniel and Remi both, and let's give them both an enormous applause. And Daniel, thank you for giving us so much of your time today.
Oh, thank you. It's been a real pleasure, and I hope some of you guys, Mike and Michael Perrone and Tom Vallone, look me up again. I'd like to make contact, and anyone else. And Remi, you owe me a phone call.
Well, and thank you to you both. So let's do this. So we'll do about half an hour of open discussion, and actually at some point, Mark Sokol, and Mark isn't even with us. Let's see if Jeremy is still with us. Jeremy, let me ask you. Okay. Yeah. So we should touch base on the conference, because I think that's actually what's coming up next. And you guys, again, you guys are present on site. Do you want to kind of give me a heads up on your plans?
Yeah, so I just let a couple people know downstairs. I think Mark just went downstairs to try and recruit some the propulsion people here from the conference to come on and talk about what was presented here at APEC this week, and will be presented. Some of this, John Brandenburg's also presenting tomorrow with the Kepler Space Group, and we're trying to get some of those guys up here for a discussion too on some of the things we've been talking about here. Every day here has been awesome, man. It's like having breakfast it's like having conference every day here, but with a whole group of people live. So we've been having breakfast with these guys like every morning and having these great conversations and stuff. So hopefully we can share some of those ideas and some of that information and what we're learning here with you all. Mark is presently going out, and we have everyone. I told a bunch of people already to be here for 5:30 for local time for when we start that up. So they'll be here.
Okay. Yeah, and so that's just about half an hour then. But I definitely did want to touch base, and so this part of it really is this. I mean, this whole part of the conference really involves you guys, and I guess we'll just go. When Mark and I were talking about this, and yourself as well, it was kind of like, okay, well, when we reach that point where they can start doing stuff from TeslaTech, it's their ball game. So, we'll hand it over to you and just see kind of what you guys can come up with. So I guess, yeah, and we can continue to do kind of open discussion for the next, half an hour or so. As I understand things, their presentations let out right around now. And so people are coming out of conference sessions at TeslaTech. And I think Mark wanted an extra half an hour just so that people could kind of get settled in and all of that stuff. Well, I guess I should ask if we're kind of in a holding pattern for a little bit, if Tom Vallone is still with us. Oops. Oh, it looks like Tom left. Oh no, there he is. Tom, did you want to demonstrate the motor that you had earlier, the spiral Wankel motor? Tom may have stepped away. It looks like he's muted and his camera is off. But okay, and I should ask. So in terms of, oops. Yeah. Okay. Sorry, kind of stalled out here. In terms of open discussion, does anybody have anything they would like to share? I guess.
I still had a few more things.
Okay. Yeah. Go for it. Yeah. I don't want to take any more of Daniel's time unless he's.
Okay. I mean, we can correspond via email anyways. But just generally for the group, I wanted to go over ergodicity in a little more concrete terms. So ergodicity, for those who are not familiar, is the assumption that all the states in a system have roughly an equal probability of being reached. So if you imagine a matrix multiplication, all of the rows and columns all add up to 1, and like the vector that you'd multiply by, or the, what was it?
Mhm.
No, I don't know. This is kind of off the cuff, so I'll
Oh, it's okay. Well,
get it wrong. But what was so
So Michael, why don't, in terms of ergoticity, let's just say you have a blank room.
well,
and you're wandering around
in different, because we can describe it in physical analogies, but I want to, for more mathematical folks, I'm trying to put it in terms of matrices.
Okay,
That's okay, because the more ways you can describe it, the clearer it will be for people. That's the idea, at least.
Isn't easier to describe it in phase space? The idea that you have trajectories which will then spread. So like Lipovanoff exponents.
For some people, but the largest sort of audience of people who can actually do something with this information is probably college level. So I'm going with matrices, if that's okay.
Okay.
But I mean, if you imagine there's an object called a Markov chain. It's a matrix that you multiply by itself many times, and it has this property that all the rows and columns add up to 1, which means that if you sum everything, it's a conserved quantity. So when you multiply it by itself, it will either oscillate or stay random, or it will converge to a single state. And in the state where it converges to a single state, it's called an absorbing Markov chain. Or you can also kind of think of it in terms of Lagrangians or whatever. It minimizes the action and energy or whatever. Action, I think. Anyway, yeah, if there's a state in that system that just eventually catches all of the energy or number or whatever term you're talking about, then that is called an absorbing Markov chain. Specifically, ergodic systems are systems that do not converge to that, are not absorbing Markov chains, to put it very concretely. And also I think they're not oscillatory systems, but that's a slightly higher level thing to talk about. So you can just show this very simply. If you have maybe a wind turbine and a battery, if you harvest some wind, put it into the battery, the probability that energy will just come out of the battery and go back into the rest of the system is much lower than the probability that the wind turbine will capture that energy and put it in the battery. That's kind of why the whole thing is practical from an engineering perspective. But I mean, it's not a perfect example, but it puts it in very simple terms. Like that's not an ergodic system, because the probability of going back from the battery into the wind is lower. I mean, depending on how you engineer the thing, you could just run the generator backwards and produce wind. But depending on how you engineer the thing, the probability is lower that it would go back into the rest of the system, and therefore it is an absorbing system, in a sense.
Well, but Tom, that's Michael, that's also a driven system. Okay.
Yes.
So
it's not a great example, but yeah.
Driven systems can do what they want.
Yeah.
So if you have a closed system that's ergodic, the analogy I was trying to make is, let's say you have a closed room and you have a person walking around the room. If they wander randomly around the room, they're going to get arbitrarily close to any point in that room on the floor eventually, and they will come arbitrarily close to any point you choose. And so ergodicity theory predicts such things, that if the system's ergodic, it will come into the vicinity of any phase space point that you wish in a sufficient amount of time.
Yeah.
But the thing is that if you've been wandering around this room all day long and have basically touched every single square inch of that room, that's fine and good. But what if somebody opens a door that you hadn't seen before in the next room? Then you can start wandering that room again, and you'll be stuck there for a while, but then you'll come back to the first room, back and forth, by simply shifting the boundary conditions slightly. In other words, turning a knob on a room, on a door of a room, you can change the behavior of that system enormously. And even at equilibrium, you can do that. There are, by subtle shifts in boundary conditions of equilibrium systems, you can go from one metastable state to another, and simply by opening and closing a door appropriately, you can get that system from a higher to a lower energy state and then back again.
Well, that's
And
the example. Oh, sorry.
Go ahead. No, go ahead.
That's the example of the Maxwell's demon, sort of. You can choose when to open and close the door in order to like make a temperature differential between the two rooms.
That's correct. But the Maxwell demon itself has too many other problems to accomplish that. That's why it's a bad example from the get-go.
Well, I mean, it's an incomplete example because what all of these systems, if I can put it a different way, like phase changes, et cetera, all of these systems are systems that capture corpuscles of energy if they achieve if they go to a certain state, not when. So a Maxwell's demon is like, when it reaches this, I open a door, it goes through.
Sure.
Well, these are not, they don't need to be intelligent because it's a different statement. It is if a corpuscle energy comes here, then it is captured. It's a Markov chain. It's an absorbing Markov chain.
Right.
And the interesting thing is you may actually, there may, for those people who are just terrified of losing the concept of entropy from thermodynamics, there may actually be an interesting thing you can do here. You're essentially taking a system that has entropy in space and turning it into a system which has entropy in a time series, because you have all these particles that bouncing around a room, and they will at some time be captured.
Oh, I should probably see if Remi has his hand up. Remi, did you want to jump in?
I just wanted to ask the crowd, the thermodynamicists, what they think of the notion that we are living entities. Life itself violates the second law. There are many processes across cell membranes and so forth. It's been said, I think, since Schrodinger, from what is life, to Mei Wang Ho is another one. Maybe Dan, I mean, what do you think that we are living embodiments of violations of the second law? I mean, it's awfully ironic, isn't it?
Well, you're addressing me? No, I think. Well, let me answer it in two ways. First of all, I suggest anyone who's interested in this problem look at the work of James Lee at the Old Dominion University, who has been looking at the behavior of cellular membranes and how they may be undermining the second, some of their actions undermining the second law. This is recently published work. So he's been working on this problem. I proposed something similar back in 2007 with article on thermosynthetic life. But in general, we are the second law's greatest creation. After all, we move around the world extracting energy and turning it into entropy. We blow up atomic bombs. We run our cars. I mean, if we were all dead, the universe would be a lot less messy than it currently is. So on its face, we are the best friends of the second law, and life is in general, because it basically takes energy and degrades it into heat. Anything you do in the world to clean it up only makes it worse. I mean, I used to argue with my mom that I shouldn't clean my room because doing so would create more universal entropy, and therefore I should be excused from cleaning up. That didn't wash with her. It would have washed with my dad, who was a physical chemist, but not with her. So there's no winning against the second law in general. You have to contrive a machine to do it.
It's the Pyrogene, isn't it? It's the Pyrogene notion and the Onsaga notion of this irreversible thermodynamics and how macroscopic flows allow spontaneous order to form in the system. That's one aspect.
But they're dissipated. Those are dissipated. They generate entropy nonetheless.
Yeah.
Okay, I have an idea. Let's make one of these systems and have it feed a container with geobacter bacteria that can harvest electrons from a potential. Just have a negative entropy system which sustains a bunch of life. In principle, something could evolve that is a negative entropy life, which is weird to think about. But I mean, just slap an organ in a system that can do this, and I see no reason why you couldn't have that.
So Tom, I mean, Michael, can you expand on that a bit? What are you proposing, and you've kind of sketched something, but incompletely.
Sorry, yes. I mean, if there's a bacterium called Geobacter, it usually in nature gets energy from rusting metal, but you can keep it alive by just having it on the appropriate electrode in water.
Right.
And then we'll just strip electrons off a surface or whatever, or donate electrons to a surface or whatever the process was, I forget. but then it can turn that into ATP and glucose and things. In principle, you could just have a little electrolytic cell keeping these bacteria alive off of ambient heat without a temperature differential. You could prove that life can exist without being a second law system.
I disagree. I disagree with that. I mean, you're turning chemical energy in a battery into maybe biological ATP energy, but you're still making an energy conversion here, which seems to comport with basic thermodynamic law. I don't see how it doesn't do so.
What I'm saying is, there's no reason an organism couldn't evolve. Like, imagine if that geobacter thing were a multicellular creature that can evolve that organelle that is a negative entropy system. Then, I mean, there's nothing in principle that prevents life from being able to harvest ambient heat, if you can harvest ambient heat at all.
Yeah, no, I think such life, if you read James Lee's work, he would claim it's already been done. I would argue that, yeah, probably life has found a way to do it, maybe. I propose it would be some sort of hypothermal file, barophile, probably found deep in the earth where there aren't good free energy sources. There are so many free energy sources where we are right now, plenty of rusty nails, plenty of hydrothermal vents, plenty of sunlight. There's plenty of free energy sources that trying to live off the scraps, which would be thermal energy, would be a mug's game, and probably would not be favored for natural selection, by natural selection. But I see no reason why it couldn't be done.
It is interesting. I mean, biological processes. I haven't read about energy generation so much, but I did read an interesting article about photosynthesis requiring quantum processes. And then, of course, there's the Penrose, Roger Penrose work, where they were assuming that the microtubules might be doing quantum computing inside of cells. And so it does intrigue me that evolution has provided us with, I think, a lot more complexity in biological systems than we at first thought.
Oh, yeah. I mean, anything we can come up with, nature has done it better probably a billion years ago.
Yeah.
So, probably pretty much the case. Well, I have to go at this point. I want to thank you guys for the opportunity here, and it's good to see some of you guys again, like Remi, and meet new people. So, Tim, thank you very much.
Yes. Well, Daniel, I can't thank you enough. Thank you so much for joining us and presenting today, and for all of your help with the questions, for all of your time as well. So,
okay, my pleasure. Okay, bye-bye.
Okay. Well, so why don't we, let me see. Why don't we hand things over to Mark?